Good morning, everybody. Today we're going to start frequency response. This is a bit of a shift from what we have seen up to this point. All the analysis we did were mostly focused on time domain. We were interested in how a system reacts to a specific input, and then it would look at how the system would response would evolve over time. So we are working on the time domain and looking at the time response. Now we're going to look at how systems respond in the frequency domain. We're going to look at their frequency response instead. Why is this important? Well, most systems, electromechanical systems, at one point can be subjected to a periodic input signal. And in that sense, the shape of the time response is pretty much known, but we want to know the magnitude or the phase of that response. And the analysis we're going to see today will help with that. The shape being known, there are other elements of that of the response of the system that we can focus on. You can think about it in a electrical circuit. For example, if you apply a DC voltage, you know that you have one transient and one time response. If you replace that with the AC with a periodic signal, then you know that the output of the system depends on the input frequency. The impedance of that system depends on the frequency, and what you get in the output is also a function of the frequency. If you think about a robot, for example, that is doing pick and place tasks, just taking an object from one place, putting it into another, like in an assembly line, for example, it's the same story. That motion is periodic. What you're telling the robot to do is a periodic signal. And the robot has a limit on how fast it can do it. If we ask the robot to go too fast, it may not have enough power to reach the end positions that we want it to go to. So all this limits, all this behavior when the sinusoid, when the excitation is a periodic signal, we can analyze using the methods we're going to see today. And this is the first lecture towards building Bode plots. We are supposed to have a Bode plot lecture today, but looking at the contents last night, I thought would be best to split that into two, because this is really one of the concepts that the students struggle the most. So let's take the time today to set the basis, and then next lecture we're going to do the Bode plots. You've probably seen Bode plots before in electronics, I think, in electrical circuit somewhere, yeah. Okay. But some people haven't seen them, and they can be a bit overwhelming at first. So let's just start with frequency response, and then next lecture we're going to jump into that. Okay, so by the end of today's lecture, we should be able to understand the concept of frequency response, determine the magnitude and the phase of a transfer function. Pretty simple. So a few applications before we go there. I gave you some examples already, but here is one. Let's assume that we had an unknown dynamic system. That dynamic system has a transfer function g of s, and we don't know what that function is because the system is hard to model, or it's just like an electrical circuit that has an input and output. You don't know what is inside. We applied a sinusoidal input to it on one side and got a sinusoidal input on the other side, and we created this plot that now relates the magnitude of the ratio between these two signals as a function of frequency. And you can measure this with the oscilloscope, for example. Based on this graph here, what can we infer about the system? Can we, for example, determine its transfer function based on that graph, based on the ratio between the input and output when the input is a sinusoidal waveform at various frequencies? And we can indeed. This is sufficient to experimentally determine the function g of s without knowing anything about the system itself. We can tell from this that it has 1, 0, and 2 poles, for example. We'll see that later, and you'll see where exactly these zeros and poles are placed and how we are going to calculate the transfer function. So this is a good problem, good application in characterizing a system, and in industrial applications is most of the time what you're going to use is this type of analysis. The advantage here is all you need really is an oscilloscope or something to measure the output of the system, and through that we can infer g of s without even having to know anything about the system. Here's another application. Here we are analyzing the electrical impedance of the tissue at various frequencies. This is called electrical impedance spectroscopy. And through that, basically what we're doing here is we're applying a current at a given frequency, and we measure the voltage, induced voltage in the tissue. And then we create these plots that will give the ratio between the input and output at various frequencies. These are the Bode plots of different tissue types. And you can see the different tissue types here. Each line is one tissue. Has different characteristics, different phases, different magnitudes. The response is different. And based on this information, we can infer what kind of tissue we are dealing with. This was a project that was running in my lab. We instrumented needles to measure the electrical impedance of the tissue. And then based on these graphs here, we can infer what type of tissue the needle is inserted in. And we can even go as far as determining if the tissue is cancerous or not based on their electrical impedance signature. Okay, so let's get into the theory a little bit. So what is the frequency response? Well, the frequency response is the response of the system when the input is a periodic signal at various frequencies. A lot of electromechanical systems are subjected to such types of inputs, as we just briefly mentioned. So here we have a process G of S. We give this process a sinusoidal waveform, and you see what happens in the output. If G of S is a linear time invariant system, and the input is a sinusoidal waveform, the output is also a sinusoidal waveform with same shape, but different magnitude and different frequency in the output, but with a magnitude that is different and perhaps a phase shift compared to the input. And that is the main reason why we always do frequency response using sinusoidal excitations, because that's the only type of periodic signal that when passed through a linear time invariant system results in the exact same shape in the output. If the input is a sine wave, the output is also a sine wave, same magnitude, but different phase and different magnitude. And what is that phase shift and that magnitude change? Well, that depends on the process G of S. That is a characteristic intrinsic to G of S. So the magnitude here, the principle is that the magnitude and the phase of that function G of S, we're going to see what that means later, is what will determine how the process reacts to that input. The ratio between the input and the output here depends on the magnitude of G of S and the phase of G of S. So if you are able to calculate that, we know the output of the system when we know the input frequency. That's sufficient. But let's let's go through a practical example first. See what do we actually want to do here. Let's consider this system. We have a mass that lies on a surface, and this mass is connected to a motor, to a pulley system like that. And you are giving this mass the motor a voltage, sinusoidal voltage as the input. So as we apply a voltage to the motor, it applies a force to the mass, and then the mass will slide on that plane. Let's assume there is friction here between the mass and the ground. And let's assume that this voltage that we apply to the motor here, V of t, is a sinusoidal voltage, and it will result in a sinusoidal force being applied to that mass. So if it is a sinusoidal voltage, the mass will go to the left and to the right, it will oscillate, right? And depending how far it goes, it depends on the frequency of those oscillations. So if the frequency of the input force is a sinusoidal waveform, so is the output, so is the displacement or the position of that mass. Now let's see what happens when we change that frequency. For simplicity, I just told you that we are always using sinusoidal waveforms, but for simplicity, let me use a square wave, just to make my point a bit more clear. So that's the force that we are applying to the mass. This force comes from the voltage applied to the motor. And what is happening here? So when you apply a force to this mass, this is a mass damper system. We could have a transfer function that will give, if we are interested in the speed of the system, there would be something like the magnitude of the force divided by Js plus B. Ms plus B. This is a translational system. Ms plus B. There's only friction in there. And now let's give this system a force f of t as we see there and see what the output is. If that is the force, what is the speed that we get in the output? Let's look at the speed first. Well, we are applying a force to this system. The speed will start to increase and eventually reach a plateau. And this plateau is F over B, provided that the system has sufficient time to reach steady state. Now look at our excitation voltage here. We have a period of, let's say, let's call this time T1 and this time T2. The period of that system is T1 plus T2. The frequency is 1 over T1 plus T2. Between 0 and T1, the force is positive. The mass moves, let's say, to the right. If T1 is sufficiently large, then the system reaches a steady state. And when it does so, the final volt speed is F over B. Is that clear? What is capping the speed here? Why it can go beyond F over B? It's friction, right? The faster it goes, the more frictional force that is. At one point, they balance out, and that's why it reaches a steady state. And when you reach T1, then we now reverse the voltage, which means that the force reverses and the system now speeds up in the opposite direction. T1 here is equal to T2. All right, so the system will now go from F over B to negative F over B. And again, this is under the assumption that we are giving the system sufficient time to reach a steady state. Right, sufficient time to reach a steady state. And then the voltage goes back positive. The system repeats its behavior, and it keeps going like that. Right. So we gave this system a particular input frequency, which is 1 over T1 plus T2. The maximum value we got in the output was F over B. We can now take this information and plot that in a separate graph. In this graph, now the y-axis is the ratio between the input and the output, and the x-axis is the frequency of excitation, frequency of this signal, 1 over T1 plus T2. What happens, so if we were here, let's call this frequency F1. At frequency F1, we got a value of F over B. That's the maximum speed that the mass has reached. What happens if we decrease the frequency? If we decrease the frequency, we are basically taking the blue curve there, and you are stretching it to the right. Or just making T1 and T2 larger. Is that clear? If you decrease the frequency, we stretch the curve to the right. T1 and T2 increase. Yeah? No? So what is the frequency? The frequency is how fast it changes direction. Right? If we give it a more time between different positive and negative, we are decreasing the frequency. We are making it slower. Right? So to decrease the frequency, T1 and T2 must shift to the right. Must shift to the right. Yeah? Does that make sense? Yeah? Okay. What happens to the speed? What is the maximum speed we reach? Is still F over B. It doesn't change. So if we decrease the frequency, we are still giving the system sufficient time to reach a steady state. So it doesn't matter how small, how much we decrease the frequency, we will always reach that plateau F over B, because you're giving the system more time to speed in one direction, speed up in one direction, but it's always capped at F over B. It cannot go faster than that. Right? But now let's consider the other case. Let's assume that we want this voltage to change faster over time. We want the system to start to bounce back and forth at a higher frequency. That means that now we are squeezing the blue curve to the right. We are making these changes in voltage, in speed happen faster. And that means now that we are giving the system less and less time to change direction. Let's for example consider that this is the signal now. You see, this is pretty much half of T1 and half of T2. You're giving the system half of the time you had to speed up in one direction and then speed up back in the other direction. What happens to the time response? Well, if we are now not giving enough time for the system to reach a steady state, then we are not going to reach its maximum speed. Instead, we shall see something like this. Now, we are just going up here, and we are reaching T1, and then we reach the new T1, we go back down. And when we reach T2, we go back up, and so on. So you see here that because the system has to change speed faster, it doesn't have sufficient time to reach a steady state. It will reach a lower speed because it now has to change back and forth. And that continues. And that will continue so long as we keep increasing the frequency. The more we increase the frequency, the lower the maximum speed is. So we could plot these new points here, and we should see something like that. What happens right here? What is making this shift go from that plateau to that specific point where now we see a decrease in the output magnitude? So we are showing this graph here, is speed over force, magnitude of the force. So that didn't change. It's still A in this case, whatever that is. We are reaching a lower and lower speed. That's why it's decreasing. So what is kicking in at this point? Well, that's the dynamics of the system. That's where the inertia and friction play a role. If we go slowly, well, the system has sufficient time to speed up and overcome inertia and reach its maximum speed. But now the faster we make it go back and forth, inertia comes in the way. And then we don't have sufficient power to make the system reach the same final speed. And that specific point here, we're going to call that later a cutoff frequency, is a frequency that it will come from the dynamics of the system itself. Okay. So if we are, let's say, right here, we have to operate at this frequency. Let's call frequency F2 here. Let's assume that this mass is that example I gave you as a robot picking and placing things in an assembly line. And you want this robot to do that really fast at a frequency F2, which is beyond the point now where we can reach the steady state value. What do we do? Well, we need to increase the power delivered to it. We need to increase the value of A. We have to increase how much the magnitude of the force we give to it. And then hopefully that it will compensate for the that lack of responsiveness in the system. Right? So through this graph, we can see the limits of our system. We can see which magnitude we would need to apply to it in order to reach a given maximum speed in the output. So this is what later we'll be referring to as a Bode plot. It's a more advanced version of this, but that's the idea. Sorry, I only caught the first part. When you introduce friction? Yes, so if you decrease the cutoff frequency, let's think about it. If we decrease inertia, in which way should the cutoff frequency change? Should I go to the left? Should I go to the right? Right? Should make the system more responsive. Yeah. Very good. Now let's look at another example here. As the same system, and now the output is the displacement. So given the system, a displacement is a bit different because now what happens? There is no limit. If we turn the system on for 10 seconds, it will spin in one direction. It will start going in one direction. Let's say it reaches 1 meter. if you double the time we let it move, it will double the displacement if the system is linear. So 1 second, let's say, it would move by 10 meters, 2 seconds, it moves by 20 meters, 3 seconds, and it will increase and so on. So the more time we give to this system to move in one direction or the other, the higher the displacement. It never stops. The time response should look like something like this, with a little transient and then always increasing. Right? The more time we give the system to spin in one direction, the farther it will travel, unlike the voltage. So what do we see in the response here if you now plot the position over the magnitude of the force? Well, we should see something that decreases over time, because as we increase the frequency, we are making it travel back and forth faster, and therefore we'll reach a lower position. We are not giving it enough time, or less and less time for it to travel in one direction. And at one point, this will get worse, because now inertia gets in the way. The same thing happened to speed, and this slope here will now increase, and it will go down faster. And that point, when we see the slope changing, that's where the inertia and friction, the inertia and friction, mass and the friction, will start to play a significant role in the time response. Right? So when we talk about frequency response, this is the type of behavior we are looking for. Is a graph that characterizes how the system responds to a given command. Now, we don't need to do this analysis every time. There are easier ways to infer the output of the system for a sinusoidal input. Look at our time response there, x of t. That there's little information there, because we know what kind of response we should get. It's always the same, right? It's always the same. It will follow that exact behavior all the time, and then you repeat. So instead, you can just look at the magnitude. If you're only interested in magnitude, then there is an easy way to do that. The other thing that you might be interested in is the phase shift that occurs between the input and output. And what do I mean by phase shift here? Well, phase shift is how in phase the output is with the input. Let's go back to the speed here. Actually, yeah, the speed is more obvious. When you're going slowly, when you change the direction of the force, let's put it this way, the response of the system will follow exactly the input waveform. That is to say, the maximum value of the output will be when the maximum value of the input occurs. It will follow that strictly, and if you go slowly. But now, if you're going faster, we can't just change the direction of motion instantaneously because of inertia, which means that when we change direction in the force, the mass is still moving in the other way. We are telling the system to go to the right, but it's actually still going to the left because of inertia. And only after it stops and it will come back, the force is now maybe already has changed direction again. So there is a delay between the response of the system and the input. It's not instantaneous past a given frequency because of the fact of inertia. And that delay is what we call the phase shift. Now that would be in the input, would just be characterized by a phase added to the sinusoidal waveform in the input, in the output. Okay, so these are basically the two characteristics that are sufficient to understand how the system responds. The ratio of the input to the output, the maximum output, and the phase shift that occurs between them. Okay. Now I used here a square wave. The problem with a square wave is that we don't get a square wave in the output. You see, the output is something else. That's why you're going to go back to a sinusoidal waveform, because if you apply a sinusoidal waveform, then the output of the system, provided that it is a linear time invariant system, is also a sinusoidal waveform, which makes this comparison a lot easier to make, because you're now dealing with sinusoidal inputs and sinusoidal outputs. So all frequency response analysis will be done using sinusoidal waveforms. And why again? because that's the only signal that when passed through a linear time invariant system results in the same signal, but with a time delay, a phase shift, and a magnitude shift. So let's go back to our system, our cart there, our mass, and let's assume that that was the process that was G of S. We had a transfer function that characterizes that system, and we have now a input U and output Y. So that's the relation between them. That's equation 1, simply the transfer function. If we are giving this system a sinusoidal waveform, then the input is in the form of a sine of omega t, omega 0 t. Omega 0 is the frequency. When you take the Laplace transform of that, we have omega 0 s squared plus omega 0 squared. If you now want to calculate the output of the system, we simply have to multiply the transfer function by the sinusoidal input. That's what we get, nothing new here. And now we can take the inverse Laplace transform. If you want to solve for the inverse Laplace transform, in our example, G of S had real poles. And the input function now, omega 0 divided by s squared plus omega 0 squared, only has imaginary poles. Now we have a combination of real poles and purely imaginary poles. Real poles coming from the transfer function, purely imaginary poles coming from the excitation input. To take the inverse Laplace transform, you're going to now have to split this into partial fractions. Some partial fractions will have now imaginary components in the roots here. We didn't do it this way because it's more complicated, but we can certainly do it that way. And when you take the inverse Laplace transform, what do we see? We see two things. We see sinusoidal components and we see exponential components. Well, that's not surprising, because if the transfer function had partial fractions with exponential components or with real poles, that it would indeed result in exponential components. And because the transfer function has poles that are purely imaginary, it will also result in sinusoidal components. So these are the two elements in the transfer function. We also have a phase shift that we can calculate here. The phase shift is simply the imaginary part of the transfer function divided by its real part. We'll see that in more detail later. But that is the phase shift in the output, the inverse tangent of the imaginary part of the transfer function divided by its real part. So we'll go back to that later, but let's focus on this now. This is the time response. And the time response has both sinusoidal and exponential components. Assuming that the system is stable, what happens to the exponential components? If the system is stable, what is the final value of the exponential components? They must decay to 0. If the system is stable, that means P1 is smaller than 0, so is P2, so is Pn. So all these exponentials eventually die out to 0. And we are left with one term here that it doesn't have any exponential component on it, only has a sinusoidal component. And that's now the steady state value of the output. The exponentials are coming from the real part. They will decay. That's the transient. And the output of the system is simply this in a steady state. Now let's see what happens here in the output. We now converted the output into a sinusoidal waveform. Two things happen here. We see a change in magnitude. We see 2 alpha 0. These are constants that appeared here. So the magnitude has changed. And we also see the appearance of this sign, this phi here, which is a phase shift. Now, we don't need to calculate this all the time because equation 10 has all what we need. This expression can be expressed as in the format of equation 10, where A is the magnitude of the input. A is the magnitude of the input. And here comes the trick. M is the magnitude of the transfer function at that particular frequency. M is the magnitude of the transfer function at the particular frequency of excitation theta omega 0. And phi here is the phase shift that I can also calculate based on the phase of the transfer function at that particular frequency. So we don't need to do this analysis all the time. All we need to know here is the magnitude of the transfer function at that frequency and the phase of the transfer function at that frequency. And that is sufficient to find exactly how the system behaves in a steady state, provided that the input is a sinusoidal excitation. How do we calculate n and phi? Oh, here it is. We'll do examples later. But what we are going to do is to evaluate the transfer function at the frequency of excitation and determine its phase and its magnitude. Every transfer function will have a real and imaginary part. The magnitude of the transfer function is the square root of the real part plus the square root of the real part squared plus the imaginary part squared. And the phase of the transfer function is the inverse tangent of the imaginary part divided by the real part. So by knowing these, we can basically determine how the system responds. So to put a visual idea here, if we take any transfer function, the transfer function has a real and an imaginary part. The distance here from the center of the S-plane to the point is the magnitude. And that is just the square root of real plus imaginary, both squared, isn't it? And the angle, the phase, is simply this angle here, which can be calculated as the inverse tangent of the real divided by the imaginary part. That's where it comes from. Okay, so any transfer function will have a real and imaginary component. How do we find this? Well, we just take the transfer function and replace S with j omega. Replace S with j omega. J is the complex variable, omega is the frequency, and then we evaluate the function at j omega. But then you may say, hold on, isn't S sigma plus j omega? I've been telling you since the beginning that S is sigma plus j omega. What happened to sigma? Any ideas why we don't use sigma anymore? Any guesses? Because sigma is the real part, and the real part causes exponentials, causes transients. So if you're only dealing with the steady state, why bother? Just take sigma away. Instead of calculating the whole thing, make the real part go to 0. Just don't even include the real part. Just forget about sigma, because it only causes transient. In the example we had, this is the type of response we would see. We see both a transient happening here, and then we see this steady state value happening there. So this is a function of sigma and omega, and this is only a function of omega, only a function of the frequency. So if you want to get rid of transients, don't include sigma. Just look at omega, and that's the whole point. That's why S equals to j omega only. Okay? Any questions so far? Any questions? Any questions from home? No good? Okay. So to determine the output of a system, given a sinusoidal input, we only need to know two things. We need to know the magnitude of that function at the frequency of excitation and the phase of that function at the frequency of excitation. And then you can get the output for as this expression here, where A is the magnitude of the input, M is the magnitude of the transfer function, phi is the phase of the transfer function. We'll see how to calculate those in a bit. Right? But again, now our S in the frequency domain is just j omega. Sigma is 0 because it would only cause transients, and we are not interested in transients. We are interested in steady state. So what are we doing here? Once again, we are taking now S equals to J omega. So if you place S in the imaginary plane here, we have S over there. This distance here is the frequency. We are giving this frequency to the system, and the output is something that the transfer function making the transfer function have a real and an imaginary component. This distance is the magnitude. We can simply calculate this with the real part is squared plus the imaginary part is squared. And this angle here is simply the inverse tangent of the imaginary divided by the real part. And all of these are frequency dependent. If we increase the frequency, then that a point on the left goes up, right? And then on the right here, we see that a point will maybe change in magnitude. If the magnitude increases, it gets farther away from zero. And if the frequency, the phase increases, then the slope tends to a vertical line. It still doesn't answer the question how you calculate this phase and magnitude, but we'll see it soon. So let me give you an example here. Consider this system. These are the same system. One is time domain, one is frequency domain. We have x of t as the input, y of t is the output. And we are given this system a sinusoidal excitation sine of 0.5t. What is the frequency? Well, the frequency is 0.5 radians per second. That's the frequency of input. That's 0 omega 0. We want to know the output of this system. So let's do this both ways. Let's do this the hard way by calculating the inverse Laplace and all that. And let's do this using the tools we just learned. What is the output equation here? Well, the output equation y of t is simply 2 times x plus integral of x dt. Yeah? And on the other side, y of s is simply the Laplace transform is x of s times 2 plus 1 over s x of s. These two are exactly the same. Let's focus on the first one. We want y of t. We know x of t. It's an input, it's a sinusoidal input. So just to replace the sinusoidal input, there we get y of t. And now we can solve for the integral. When solve for the integral, we get that. We can simplify this. Now we can use a trigonometric identity that I have to look up here. I didn't remember this, so I don't expect you to remember that either. It's just a trigonometric identity. We go from 2 sines of same sine and cosine of same frequency to just the 1 sine wave. And when you apply that trigonometric identity, you can check that later. This is the result of the manipulation. Y of t is also a sinusoidal waveform. Y of t is at the same frequency of the input. You see 0.5t is still there, but 2 things have changed. There is a constant in front of the sign, and there is also phase shift. Based on this result, tell me, what is the magnitude of the function at 0.5 radians per second? See if you're following. What is the magnitude of the transfer function? Y over x at 0.5 radians per second. What do we expect to see in the output? Well, we expect to see y of t equals to am sine of omega t plus phi. What is A? A is the magnitude of the input. In this case, is 1. What is M? M is the magnitude of the transfer function at the particular frequency of excitation. Based on the result you got at the bottom there, what is M? 2 square root of 2. That is scaling factor. That is scaling factor is the magnitude of the transfer function. And what is the phase of the transfer function? Well, that's what appeared in the sign there, negative 0.785 radians. That's the phase of the transfer function. This is to say that if you now take the second approach here and calculate the phase and the magnitude of that at that particular frequency, we must find a magnitude of 2 square root of 2, and you must find a frequency, a phase of 0.785 radians per second. So let's do that next. Here is the expression for that part. Nothing new here. Now we're going to evaluate the transfer function, magnitude, and phase at 0.5 radians per second, because that's the excitation frequency. If that is the case, then then S is omega j. S is 0.5 j. And we can now replace S with the 0.5 j in there. Okay, so we have 2 plus 1 over 0.5 j. That 1 over j is not easy to handle, so we're going to get rid of it. And to get rid of it, we just multiply the top and the bottom of the equation by j. That's the complex number. All right, so j is the square root of negative 1. Sorry, square root of negative 1. By doing that, we're just getting rid of the j in the denominator, moving that to the numerator. So we have 1 times j, that's j. And we have 1 over 0.5, that's 2. And what is j times j? Negative 1, right? Negative 1. J times j is negative 1. So the result of this operation here is 1 over 5, that's 1 over 0.5, that's 2 times j, and times negative 1, because j times j is square root of negative 1, square root of negative 1, and that's negative 1. And square root of negative 1 is squared, put it this way, which is negative 1. So the result of this manipulation is here. 2 minus 2j. And there we can see the real part of the transfer function, that's 2. And you can see the imaginary part of the transfer function, which is negative 2. Then the imaginary part of the transfer function is not negative 2j. J is just the coordinate is negative 2. So now we can calculate the phase and magnitude based on the approach we saw before. Real part is squared plus imaginary part is squared, square root of the sum. That's indeed square root of 2. Surprise, same thing we found before. All right. Let's find the phase. Imaginary part divided by real part, inverse tangent of that. Imaginary part is negative 2. Real part is 2. The ratio is negative 1. Inverse tangent 0.785 radians. That's exactly what we found here. Magnitude of the transfer function, phase of the transfer function. Now determine the output of the system given a sinusoidal input. Any questions? Any questions? No? Any question from home? Nobody has questions at home? Okay. When there are no questions, we'll move on. Sure? Yeah? Okay. Okay, now let's go back here and we can see that according to this analysis, the magnitude and the phase transfer function are both frequency dependent. We can take the magnitudes here. Well, we can take the transfer function expressed as a vector like that, the real and imaginary part, and plot that in the imaginary real axis. So if you look at the function here, we have a real and an imaginary part. So the real part is 2. And the imaginary part is negative 1 over omega. And you can put that over here. That's the magnitude and phase of the transfer function. That's now frequency dependent. So here's phi, and here is m. Let's analyze how this changes as the frequency goes to 0. As the frequency goes to 0, what happens to the phase of the transfer function? If frequency tends to 0, then we are having 1 over omega. Omega tends to 0. That is a very large negative number. It tends to negative infinity. So when the frequency tends to 0, what happens to the angle phi? It tends to what value? If omega is tending to 0, then negative 1 over 0 is, or something very small, is negative infinity. So the vector tends downwards, and phi tends to negative 90 degrees. And eventually becomes a straight line downwards. And the magnitude tends to infinity, because the vector keeps growing as it moves downwards. And it moves downwards towards 90 degrees, just towards a straight line down. What happens if you increase the frequency? What if the frequency tends to infinity? Then the vector shifts upwards. And what happens to the phase? What is the value of the phase? When the frequency tends to infinity, negative 1 over infinity is 0. So the imaginary part becomes 0. And you only have the real part. So the vector is pointing towards 2, meaning that the phase becomes 0 degrees. And the magnitude becomes 2, exactly, becomes 2. And that vector will oscillate there depending on the frequency we give to the system. Now, both frequency and magnitude, both magnitude and phase are frequency dependent. Okay. Now, this is a relatively simple problem to calculate the phase and the magnitude, because you only have like very clear real and very clear imaginary component. What happens if we go to a standard, a normal transfer function where you have multiple poles and multiple zeros together, and also multiplied by a gain here? Well, the good news is that you can calculate the magnitude and phase of individual poles and zeros and then use them together. If you go to equation 11, that's a function, a generic function with several poles and several zeros. If you want to calculate the phase and magnitude of this function, we can calculate the magnitude, starting with the magnitude, to calculate the magnitude of all zeros, multiply them together, and divide that by the magnitude of all poles multiplied together. So we don't need to expand that, find the real, find the imaginary part. We simply have to calculate the magnitude of each zero, multiply everybody together, divide by the multiplication of the magnitude of all poles. And same goes to the phase. If you have multiple poles and zeros, we can simply add the phase of all poles and zeros. So magnitude, the phase of all zeros added together minus the phase of all poles added together. We can calculate the individual magnitude, the individual phase. The magnitude of the whole function is the magnitude of all zeros multiplied together divided by the magnitude of all poles multiplied together. And the phase is the phase of all zeros minus the phase of all poles. It's simple. And that gives the phase of the entire transfer function. This is a bit abstract, but you see it's really simple. We'll do an example right now, unless there are questions. Any questions? No? Okay. So I'm going to do an exercise now, and now this is relatively easy. Just find the same format of to calculate the phase and magnitude and plug in numbers. That's easy. What I really wanted to understand here is why you're doing this. Why are we interested in the time response, the frequency response? What does it represent? What information do we get? What practical application do we get from it? So that's why I started with this example. In the next lecture, what we are going to do is to make these plots based on the transfer function. Make these Bode plots. And what we see in that plot is what I wanted to retain, is the ratio between input and output is how the system responds as the frequency changes. And this has a lot of practical applications. If you go later when you graduate, if you work in the industry, in control systems, you'll be using frequency response all the time to characterize a system and to control it. And it has applications really everywhere in the industry, particularly when we are dealing with system characterization and system control. Okay, so let's do one example here. Are there any questions before we begin? No? People seem to be still in their beds at this time, given the weather. We all thought that the winter was gone, but Ottawa surprises you every time. Okay, so if there are no questions, let's do this one. We have a tendon-operated robotic hand that can be implemented using a pneumatic actuator. The actuator can be represented by that transfer function. And we want to calculate the phase and magnitude of that transfer function at 10 radians per second and 200 radians per second. Why? Well, if we are doing a pneumatic actuator for a hand, the actuator may have to expand and contract. And through this, we can determine what is the maximum, for example, the maximum, if this transfer function corresponds to the ratio between the input and output, let's say a voltage input and a position output of the actuator, that will tell us how fast the actuator, when put in a robotic hand, can actually grab something and release it, how fast it can move. Depending on, based on the analysis we just saw before, if we ask the robot or the actuator to change direction too fast, it may not be able to reach its full motion, its full range of motion. It will basically just oscillate around a given point. Kind of start to shake around a little point. So that's one of the type of analysis we can see here. What is the maximum displacement we would be able to reach if you give it 10 radians per second? What is the maximum displacement it can reach if we ask it to change direction every with a frequency of 200 radians per second? Right? That's the practical analysis, practical application we can see here. So let's do that. That's the transfer function. And for a transfer function to calculate the phase and the magnitude, we can simply set S equal to J omega. Where is sigma again? Sigma is gone because that only causes transients, and we are not interested in the transients. So now I can rewrite the function as a function of J omega, 1000 divided by J omega plus 100, J omega plus 10. So this function has two poles, no zeros. In the poles here, we see the imaginary part, we see the real part, we see another imaginary part, and you see a real part. So we could multiply all these out and then find only one real and one imaginary part, and then use the tools we used before. Or we can simply use all poles instead. Now let's write this as a function of the magnitude. So to take the magnitude of the transfer function, that is the magnitude of 1000. Let's put this as 1000 plus, let's say, 0 J. So that's stuck. Okay, let me open it again. It's plus 0j. So on the top there we have square root of the real part squared plus the imaginary part squared, 0, divided by the magnitude of each pole is square root of the imaginary part squared plus the real part squared. And for the second one is the same, square root of the imaginary part squared, omega, plus real part squared, 10. Now the imaginary part, when you talk about 10j, the imaginary part is 10. It's not 10j. J is just indicating what that is, because if you square 10j, you get negative 100. If you square 10, you go to get a 100. Right? So don't make that mistake. It's a very common mistake to make. J doesn't make it. It's not part of the magnitude. It just indicates what is the imaginary part. So that's the equation for the magnitude. The equation for the phase is phase of all zeros. There are no zeros, so that's 0, minus the phase of all poles. We have 2 poles. The phase of the first one, s plus 100, is the arctangent, the inverse tangent of the imaginary part, which is omega, divided by the real part, which is 100, plus the phase of the other pole, which is arctangent of omega over 10. Omega over 10. Imaginary part divided by the real part. We can see that these two are frequency dependent. Here we have the expression for the phase, the magnitude. Here we have the expression for the phase. They are both frequency dependent. We are asked to determine this at what value is 210, right? 210. So if you do omega equals to 10, we can simply replace omega in here. That's the square root of, that's 1000 divided by square root of 10 squared plus 100 squared times square root of 10 squared plus 10 squared. And the phase is negative 10 over 100 minus 810, 10 over 10. And this gives a magnitude of 0.7035 and a phase of 0.022. This is radians. And if we can do the same for the other one, omega equals to 200, I'm not going to write this down, just give you the result here. If omega is 200, then the magnitude is 0.022, and the phase is negative 150 degrees. Sorry, I made a mistake here. I copied something else. Where the phase is negative 50.7 degrees, and the phase for the other one is negative 150. Yep. So the 0, it represents the phase of all zeros. Because there are no zeros, then I put 0 in there. Right? So sum of the phase of all zeros minus sum of the phase of all poles. Okay. Any questions? Easy, isn't it? It's not really not very complicated. No, but this kind of worries me a little bit, because when there's this simple, it's just to go play in numbers and they get the result, and then the understanding stops there. I really wanted to focus on what this is representing physically when you calculate the phase and magnitude. What is that doing to the system? What information we get in practical terms here? And this is easy. There's nothing really complicated about it. Any questions? Should we move on? Yeah. Any questions from home? No? All right. So if there are no questions, let's do another example here. We're talking about radio telescopes are used to study the radio frequency portion of the electromagnetic spectrum emitted by astronomical objects. One critical problem of driving large telescopes is the form of the system transfer function that has a structural resonance. You guys all know what a resonance is? Is when we apply a particular frequency to the system and then the output increases significantly, is where you get the highest magnitude in the output. As an example online, we have a bridge, and that bridge had a dynamic resonance. So we had troops crossing the bridge. They had to slow down their march, because if they marched at a given pace, they would vibrate the structure at the resonance frequency. So you're applying a force at a specific frequency to the structure, and then the entire structure would start to bounce and create a very large displacement. If they were running through, that wouldn't happen. If they slow down, that doesn't happen, because they are not specifically at the critical frequency of resonance. You can also think about this is some sort of swing. So you have someone sitting on a swing and you are applying a force. Every time the person comes back to you, you apply a force. If that force is applied exactly at a given time, at the appropriate time when the person comes back to you and apply a force there, then you get the maximum displacement. But if you're applying a force at any other times that is not in sync with the dynamics of the swing, then you don't get the same output. So there is one specific frequency that results in a maximum output, and that's the resonance frequency of the system. There is another example of a bridge, a cable bridge, that collapsed because of wind gusts and the the problem was that the wind was making the frequency vibrate at a specific frequency. It wasn't even a strong wind. It just so happened that it was creating a frequency of vibration that had matched the resonance frequency of the bridge, and the bridge collapsed. Right? So this is the same problem in the radio telescopes. If the wind gust creates these vibrations exactly at the same frequency, then it's very hard to maintain the position of the telescope, because it is going to vibrate at a relatively high magnitude. A large telescope with diameter of 20 meters, for example, is subjected to large wind gust torques that can affect positioning accuracy. So here is the transfer function of such telescope. This could be, for example, the relation between its desired position and its actual position. We want that to be very precise. The question is, determine the resonance frequency, knowing that the resonance frequency, at the resonance frequency, the input and the output signals are 180 degrees out of phase. Let's maybe complicate this a little bit more. Let's calculate the maximum magnitude of the displacement in the output, which would be the magnitude of the transfer function at the resonance frequency. That's what gives the maximum displacement in the output. In this case, if you're considering that this is a displacement transfer function. So to do that, we first need to calculate the resonance frequency. And here it says that the resonance frequency occurs when the input and the output signal are 180 degrees out of phase. Why is that important to us? Because, well, it is the solution to the problem. In fact, if we plot the imaginary and the real component of the transfer function, and we are 180 degrees out of phase, then it's going to be somewhere around there. So this is the imaginary, this is the real component, and this is 180 degrees. If you're saying that the resonance frequency occurs at 180 degrees phase shift between the input and output, that is the same as saying the magnitude of the transfer function, sorry, the phase of the transfer function at the resonance frequency is precisely 180 degrees. It's the same statement. So we can position that the magnitude and the phase of transfer function on the S-plane, and you see here what happens. The imaginary part becomes 0. The imaginary part becomes 0. So to find the resonance frequency, all we need to find is the frequency that leads to 0 imaginary component in the transfer function. And then you can evaluate the magnitude of the transfer function at that particular frequency. Does that make sense? Yeah? Okay, so let's do it here. What is the transfer function again? 10. Did I note? Let's look at my notes here. So G of S is 10s divided by s plus 1, s squared plus s plus 10. So when the phase and the magnitude, when the input and the output are 180 degrees out of phase, that means the phase of the transfer function is got to be 180 degrees. And once again, when you plot that on the imaginary real plane here, we see that the imaginary component is 0. So in order to find the resonance frequency, we are looking for the frequency where the phase is 180 degrees. We are looking for the frequency where the imaginary part is 0. So to do that, let's first find the real and imaginary parts. So here we have the transfer function. We can replace s with j omega. And then you have 10 j omega divided by j omega plus 1. What is j omega squared? What's j omega squared? Is negative omega squared. Negative omega squared. Right, j omega squared is that because the square root of negative 1 squared is negative 1. Okay, so negative omega squared plus j omega plus 10. We can multiply this out. 10 j omega divided by j omega times omega squared is negative j omega to the power of 3. J omega times j omega is negative omega squared. J omega plus 10 is plus 10 j omega. And then you just repeat everything. That's plus j omega plus 10. And this can be simplified to 10 j omega divided by what? Let me put the real parts here and the imaginary parts. So you have negative 2 omega squared plus 10. And then you have plus j negative power of 3, sorry, negative power of 3 and plus 11 omega. Okay, so I just factor out j here and added everything up. So there are a few steps here together. So I just added everybody up and then factor out j. Why did I do that? Well, because now we can clearly see in the denominator we have a real part and we have an imaginary part. Real part and an imaginary part. So that imaginary part in the denominator is kind of inconvenient because we don't know exactly what the magnitude of the transfer function or the real and the imaginary part of the transfer functions are. How do we get rid of this j in the denominator? Back to calculus of complex variable. How do we get rid of j in the denominator? Any guesses, any ideas? We can multiply the function by the conjugate of the denominator. Right? So if you want to get rid of that, we can simply multiply the transfer function by the conjugate of the denominator. Of course, multiply and divide otherwise we change the transfer function. So multiply this by the conjugate of the denominator. That is to say, we are changing the sign of the denominators. This should have been 3 here. Okay, and then we repeat the conjugate of the denominator like that. So I didn't change the function, just multiply it by 1. All right, but then you see that I'm taking the denominator, changing the sign of the imaginary part, and that's the conjugate of it. Why am I doing that? Because if we have a, here we have a. If here we have b, here we have negative b. And when you do a plus b times a minus b, what do we get? We get a squared minus b squared. And when we do b squared, you see j squared is negative 1. The imaginary part disappears. And the imaginary part disappears. I'll keep a and b there, but what you should take from this is that when you multiply out the denominator, we get a real number. And now the imaginary part has moved to the top of the equation. So now we can multiply the numerator out. We have gj omega equals to j times 10 omega times negative 2 omega squared plus 10 divided by a squared minus b squared. And then we have this times that. We have 10j times j. That's negative. So j times j is negative 1. We have then positive 10 omega times omega minus omega squared plus 11 omega divided by a squared minus b squared. Okay, so what happened in this process? J times j is negative 1. So 10j omega times the whole thing is simply plus 10 omega because negative j times j is plus 1. And the denominator, I just used a and b to keep this generic. Right? But the important thing to know is that they are real numbers. A and B are real numbers. So what do we see here? Now we can clearly identify the real and imaginary portions of the transfer function. Here is the imaginary part. Here is the real part. And when the phase of the transfer function is 180 degrees, what happens again? The imaginary part is 0. Let's go back to the graph. Sorry, this is stuck again. The graph here, when the phase of the transfer function is 180 degrees, the magnitude, excuse me, the phase of when the phase is 180 degrees, the imaginary part becomes 0. So we can go here, take our transfer function, and set its imaginary part to 0 to find the resonance frequency. We now have to set 10 omega minus 2 omega squared plus 10 divided by a squared minus b squared. This is 0. And now you understand why I kept a and b there, because you don't even have to calculate them, because now when you multiply a squared minus b squared by 0, that's 0. So all you have to solve for is 10 omega minus 2 omega squared plus 10 equals to 0. What are the solutions to this equation? Omega equals to 0 satisfies that equation, but this is not a valid frequency. You can't have a frequency of 0 radians per second. That's not a frequency. Or you can have negative 2 omega squared plus 10 equals to 0, and this gives omega equals to square root of 5. Radians per second. Plus minus, right? Plus minus the square root of 5. Negative frequency doesn't exist, so we stick with the positive value. So when the frequency is the square root of 5 radians per second, we reach the maximum displacement in the output, we reach the resonance frequency of the system, the telescope. If you wish to calculate the phase and magnitude of the transfer function at this frequency, we can simply go back to the equation we started from. G of j omega equals to 10 that divided by j omega plus 1 minus omega squared plus j omega plus 10. Let's calculate the magnitude here. I'll post the phase later. What is the magnitude? Is the magnitude of 10 j omega as the square root of real part 0 squared plus imaginary part squared. That's 10 omega squared divided by the square root of real part squared 1 imaginary part squared omega squared, square root of real part squared. Here is a bit tricky because it's negative omega squared plus 10. That's the real part. And the imaginary part squared is omega squared. We can now replace omega with square root of 5, and then we get the magnitude of the transfer function at that particular frequency. Let's do the phase. Actually, we have time. Just rush through the phase here. What is the phase? Is the phase of all zeros. That's A10 of imaginary part 10 omega divided by 0. Excuse me for the inaccuracy here. I can't write it that way, but you know what I mean here. This is just 90 degrees. Minus the inverse tangent of one of the zeros, one of the poles is here imaginary part omega over 1 real, and minus A10 imaginary part is omega, real part is 10 minus omega squared. All right, and then replace omega with square root of 5, and then you have the magnitude